I know that folks are still coming back, but we should get started. So I would like to welcome you all on the conference session on the optimization of radiological protection in nuclear power plants and the nuclear fuel cycle. My name is Joseph Zick, and I am the Director of Health Physics at McMaster University in Hamilton, Ontario, where we have a range of nuclear activities that we do, ranging from a small research reactor, 10 megawatts, to all sorts of other research activities related to nuclear materials. I also teach health physics at the university, both at the undergraduate and the graduate level, and also provide health physics consulting services, so working on some of the RP program developments for some of the SMR projects that we have in Ontario, and also some of the design from an RP perspective. And I'm also a member of the World Nuclear Association RP Working Group, and pleased to represent both the industry and academia here today. It is my pleasure as we start the session to introduce Scott Stafford this morning. He is the RP Program and ALARA Section Manager for the Radiation Safety Department at Darlington Nuclear Generating Station and working on the refurbishment project. As I'm sure he will tell you, it is one of the largest infrastructure projects that we have in Canada. He's been working in the nuclear field for more than 20 years, joining Ontario Power Generation as a health physicist in 2001 after obtaining his degree in medical health physics. He also has a master's degree in engineering from McMaster University, and he will be presenting the results of radiation safety optimization at the Darlington Nuclear Power Plant 4-unit refurbishment project. Scott?
Shorter. So thank you very much. I'm very much looking forward to this opportunity to go through some of the immense challenges and lessons learned we've had in our refurbishment. In order for us to help give you a fulsome presentation, I'm going to go through just a bit of a primer on OPG and on the CANDU reactor design, why it needs to be refurbished as we are doing now. And then I'll go into the refurbishment lessons learned from the Unit 2 refurbishment, which was the first one. And then currently we are almost complete the Unit 3 and how those lessons learned were applied for very substantial improvements in terms of dose and optimization. So for an OPG CANDU primer, this is a summary of Ontario Power Generation as a company located in Ontario. It's one of North America's largest and most diverse electrical generators, 18,958 megawatt capacity as a whole, which includes 2 nuclear stations, 66 hydroelectric stations, $6 billion in assets, and other facilities as mentioned here, biomass station, gas cycle. We are also have a solar facility and 87 U.S. hydroelectric stations operated by a subsidiary. We're developing, as mentioned, I think in a couple of previous presentations, Canada's first small modular reactor that is intended to be constructed and operated on the Darlington nuclear site. And we're a leading producer of nuclear medical isotopes, first harvesting said isotopes at our Pickering nuclear facility. With regards to the Darlington station where this refurbishment is taking place, this is just a bit of a summary on some of the technical details. It's an 881 megawatt reactor unit. That's a single unit. There are 4 on the site. So that's just shy of about 1 million homes of power capable for each unit on the site, and there are 4 of them. One of the more important parts is with the Canada design, which I'll go into, there's 480 fuel channels, some technical details of the pressure and temperature that the reactor operates at. It's a multi-unit design which is connected to a vacuum structure for safety purposes, and has about a net electrical output thermal power efficiency of about 31.7%. With regards to the design for the primer on CANDU, CANDU, which is a Canadian deuterium-uranium reactor, is unique in using natural uranium as its fuel as opposed to enriched uranium fuel. In a CANDU reactor, fueling is a routine operation. A pair of remotely controlled fueling machines insert new fuel and remove old fuel while the reactor is still operating at 100% full power supplying the grid. That has some advantages, such as defective fuel can be removed as soon as it's discovered. The fueling workload is distributed over the year as opposed to having to focus on a refueling outage that U.S. design plants are necessary to do for their refueling, which is every 3 years. And steady operation at full power requires about 100 to 140 fuel bundles to be removed and installed per week. About 1 dozen fuel channels. It's a very intense activity that's constantly occurring to keep the reactor running. The concentration of uranium-235 in natural uranium is low, so the number of neutrons bombarding the fuel must be high. And back in the 50s, when this design was being created, the scientists knew that in order to achieve reactor power, you needed a heavy water moderator, a D2O heavy water moderator, as any other moderator would be too efficient at absorbing neutrons and not scattering them. A large tank called a calandria with hundreds of pressure tubes within the tank, it contains the moderator. The calandria is not the pressure vessel, the fuel channels are. And the heavy water in the calandria absorbs very few neutrons, but it's not as effective at light water as slowing them down. So one of the byproducts of this design is that our reactors are physically much larger than reactors are in the United States that use enriched uranium. They are physically smaller. This just gives you an indication of the calandria. And you can see on the second picture over here that it's got the pressure tubes running through it with the moderator D2O surrounding it. So in light water moderator reactors, the moderator also serves as the coolant, but a CANDU design separates them. We have a moderator system, which is low pressure, and then we have a primary heat transport system, which is the high pressure system. This takes the heat from the reactor core and sends it to the steam generators, where it's converted through a secondary side to steam to run the turbine. The pressure tubes, as you saw, are running horizontally through the calandria and contain the fuel. This is just a diagram to give you an idea of how this looks like. I've been told by our US friends that they refer to the CANDU as the spaghetti reactor because it has hundreds and hundreds and hundreds of feeder tubes running from the steam generators to each individual channel. I've also, and they've not, their designs are not like that, so this is something new and unique from their point of view. This gives you just a basic idea of generally the scale and size. You can see the people at the bottom. To give you a sense of scale between that, the fuel the fueling machine, which is just above them, the reactor face itself, the feeders all going to various different headers, which supply the pressurized water to the steam generators above. They're fairly large size. And then I just have a couple pictures here for the Darlington reactor, which were taken during its construction days back in the late 80s, early 90s. You can see a person in the bottom left corner there, just again to give you a size of scale. And then here you can see the feeders running from each of the channels up into the common headers towards the steam generator. And up at the headers, you can see all the feeders coalescing into them at the top. So that's just a primer on how generally how the reactor looks like and how it operates. I'll now go into the first unit that we refurbished, but first I'll be going into an aspect of why we need to do this refurbishment. So the refurbishment of CANDU reactors is an aspect of their design. It was always intended that this particular activity would be necessary, as it's required at the midpoint of their operational service, approximately after the first 30 years of operation. During the refurbishment phase, major components in each reactor are inspected, serviced, and replaced. A key refurbishment activity is the removal and replacement of the fuel channel assemblies, the fuel channels themselves, and all those feeder pipes going up into the upper headers. They all must be cut out and replaced with new feeders and new fuel channels. So for the Darlington nuclear site, the DNRU2, which is the name of the project for refurbishment of Unit 2, commenced October 15th, 2016, as planned, and then took a little over 3 years and change, I think into 4 years, reached 100% full power back on the grid June 3rd, 2020. At the time, as mentioned, this was the largest infrastructure project in Canada. Don't have the specific dollar value, but it's been estimated to be about 1/3 the cost of buying Twitter. So, refurbishment for Unit 2 took 1,328 days. I will get into that was a bit longer than what was originally projected and planned for, but from the point of view of CANDO refurbishments in the past, which they've been occurring at Bruce, at Point Lepreau, and overseas, we were actually performed quite well in terms of schedule. Schedule has always been a problem when it comes to major refurbishments of this type. 400, and this gives you an idea of just how much work was involved over the 1,328 days. 480 pressure tubes and calandria tubes removed remotely, and volume reduced to thousands of coupons about the size of a Post-it note. 960 feeder tubes removed via several cut sites on each tube, and new feeder tubes installed requiring over 2,000 welds. Over 8,000 individual sealed source radiography shots were performed for the feeder installation campaign alone. 5,550 terabecquerels of radioactive material, this is core components, pressure tubes, and so on, were removed from that reactor. Approximately 2,300 kilograms of magnetite were removed from the steam generator primary side tubes in order to remove that magnetite and have them declared good for service for another 30 years. Over 801,000 electronic personal dosimeters were issued to a workforce that went as high as 2,000 at any given point. Over 450,000 reactor vault entries to perform this work. And on average, over 27,000 radiation surveys completed each year of the project, which, as mentioned, was continued on for over 3 years. So the Unit 2 project was completed with a total collective radiation exposure of just shy of 25 sievert. This is, as you can see by this graph, was higher than our original estimate. Our original estimate was in the 21 sievert range. And two main challenges to this collective radiation exposure were identified as slippage of schedule. If it takes longer, there's more exposure time. And increasing in manpower requirements compared to the original estimate. When it was determined that there was a need for, trying to get back on schedule, there was scenarios where more workers required at the site were necessary. This just gives, I won't go through this in detail, this just gives you an idea of the overall kind of main critical path planning with some specific RP aspects color-coded into it to make the RP support and RP requirements a little easy to see from a quick look point of view. The color coding has to do with the radiation protective equipment necessary, whether it be an air-supplied plastic suit, a PAPR, a negative pressure respirator, anti-seize for contamination control, and then that was the basic level of information that we had at a glance for the workforce for Unit 2. We did have some challenging RP events that had an impact on the project and whose outcome did drive some of our refurbishment decisions going forward. I'm not going to actually go through all of them, but the most important ones from our point of view are summarized here. Just going to go through one or two quick examples. We had an annulus spacer, which is, an annulus spacer is a high cobalt content piece of ring metal that's in between the pressure tube and the calandria tube. It ended up sliding onto someone's hand inadvertently as part of the work that they were doing. Resulted in elevated levels, dose rate levels in the work area, and the worker needed to back out. The dose rate alarm to the worker at that event was 0.35 sievert per hour at that instantaneous event. And the worker's EPD dose, however, for the entire jump was only 0.56 millisievert, which was low given how significant this event could be. It did require an extremity dose calculation using Monte Carlo modeling and extrapolating the extremity TLD results and whole body TLD results to validate, resulted in an extremity dose assignment of 0.166 sievert to the right hand. This is actually still going into that event. We had 2 rad technicians who were selected to recover that analyst spacer. A 10-foot specialized gripper was utilized to perform the retrieval. I apologize, this table is in imperial units. Imperial is the units that the nuclear industry tends to use. But just to give you an idea that from 1 centimeter from the spring, we were seeing, I believe that would be 30 sievert per hour. So we were seeing 30 sievert per hour, 1 centimeter from it. Peak dose rate observed by the radiation technician who was actually performing the recovery was only 4.25 millisievert an hour. This is just a quick picture that shows you where the worker had to go in, retrieve the item, put it into a flask that's in the top left. And then we had retube waste processing, shear contamination. I'm actually going to go over this one quicker. We had a piece of the component that was contaminated with, again, debris from these analyst spacers. It required it to be removed and replaced, given that there was too high dose rates from it for us to continue to use it. We did have some achievements, which again I'll go through quickly. Radiography was actually a good success story given how many radiography shots, as mentioned, that we needed to perform. And for me personally, one of our lessons learned and successes is the institution of an ALARA health physicist on shift coverage. So for a 4-year project, we had 24/7 health physicist support for all work activities performed, which was instrumental in dealing with issues and challenges immediately, as opposed to having them become larger and larger issues. So I'm running out of time, so I will now go into what how we applied those into the Unit 3 outage, which we're currently almost complete now. We will capitalize on the knowledge and experience gained from Unit 2, rely on proven strategies, develop a highly skilled radiation protection personnel at all levels, and we will specifically take our lessons from Unit 2 and apply them to Unit 3, which we did. So we took the RP plan and we enhanced it to also show anticipated rad conditions, RPP required, when open beam work was, what the expected daily dose was from a collective point of view, and how many anticipated personal contam events we might expect to see depending on the work that's occurring. We de-scoped a major activity. We had shielded a bulkhead that isolates this unit from other units. That was originally in plan for Unit 2. We ran into some challenges with the effectiveness of the shielding, so we decided not to shield for Unit 3 and evacuate the vault anytime a fueling machine needed to pass underneath. We became very efficient at doing that. But from a dose point of view, we had a very big success by a change in the method by which we removed pressure tubes and calandria tubes. Originally, they were removed separately. We now are removing them all as one piece. The calandria tube and pressure tube come out as one piece into the flask when they're removed. This has saved a tremendous amount of time and a tremendous amount of dose as well. We anticipate that it will save about 0.78 person sievert of dose and 35 days of critical path saved. We implemented the use of person-powered air purifying respirators for the workforce, as opposed to mandating they're requiring plastic suits, which are bulky and with an air hose more difficult to work with. The RPPE was well received by the workers. They're in wide use at the refurbishment projects for Darlington right now. And additionally, they reduced tripping hazards associated with the air supply use. We have initiatives with regards to shielding, reactor face shielding, header nozzle shielding, certain specific pipes that have high dose rates associated. We started utilizing magnetic shielding applied. Implemented very strongly enforced low dose waiting areas and a source term reduction review to remove as much source term, as early as possible. We performed a review as to what series constitutes high hazard work and what series may not be required high hazard oversight. We enforced a vault restriction when fueling machines going by. We enhanced and improved our material movement. And we developed RP execution guides to further assist the workers performing the work with our RP techs providing oversight to understand the nature of the hazards that could be expected depending on what work they're doing. Current status of Unit 3, all our removal activities are complete. The calandria tube and fuel channels are installed. The lower feeder installation actually was completed last week. And we are now into the return to service and unit startup phase. So if you're looking at this graph, the yellow line is the collective external dose of Unit 2. You can see in the green line, the Unit 3 dose has now come under, and we anticipate will be significantly under the Unit 2 line. And the Unit 1, which just began its refurbishment a few months ago, is tracking along the same line as the green line, so showing that we've doubled down on performing these kinds of activities in Unit 1 as well. I won't go through all of this. This is just a summary of the collective dose comparisons between Unit 2 and Unit 3. Everything green is a substantial reduction in collective dose when performed on Unit 3. So at this rate, for ALARA purposes, we have something in the industry that says, in the RP industry benchmark is, accrue $50,000 per 0.01 person sievert of dose avoided. So if you apply that formula here, we're in about 12.4 million equivalent dollars saved for dose that we've averted that we haven't had to do. And as you can see, the green line there shows you how we are in comparison to other can-do refurbishments. When you normalize the work they're doing, the number of activities they perform, number of fuel channels they have. Unit 2 did come in higher than we would have liked compared to those units, but we are now projecting much lower than the other units, and we will need to reevaluate and lower our Unit 1 target as well. 30 seconds over. And so I would like to say thank you very much.
Next up, we have Carrie Taves. She carries the program manager for occupational safety at Chemical Corporation, which includes conventional safety, industrial hygiene, and of course radiation protection, where she started her career as a health physicist more than 20 years ago. And in that capacity, she has extensive experience with all aspects of RP and the uranium mining and processing industry. Carrie?
Thank you. I appreciate the chance to have this talk, and I don't believe there are a lot of uranium miners in the crowd, so I'm going to use some practical examples to help you to understand what we do and some of the radiation protection strategies we use in high-grade mining. So first, I'm going to talk about what is high-grade mining and focus most of my talk on sources and control strategies that we use, and finally a quick look at doses at the end. First off, I work at Chemical Corporation. We're a Canadian-based uranium producer, and we operate or have ownership in 10 facilities in Canada, the United States, and Kazakhstan. Those range from mining and milling through to production of UF6 and fuel fabrication for CANDU reactors. My talk is going to focus on 3 operations in northern Saskatchewan. Those are located about 2,000 kilometers to the east of here, and I guess for reference, most uranium mines in the world are significantly below 1% uranium. When our Rabbit Lake operation first opened its underground facilities in the early 90s, it was mining between 1% and 4% uranium and was considered very high grade for its time. Since then, we've opened up our McArthur River and Cigar Lake operations in the early 2000s, and they've become the highest grade uranium mines in the world. In its last production year, McArthur was mining an average grade of 10%, and Cigar Lake an average grade of 15%. And that's just the average. Individual or small pockets can, of course, be quite high in comparison to that average. The sources of radiation at all three of those facilities are the same, but the magnitude of those sources change with grade. The first one I'll talk about is gamma radiation, and it is directly proportional to grade, with the majority of that radiation coming from the decay products of uranium, not the uranium itself. As a rule of thumb proportionality, we say 45 microsievert per hour per percent uranium for large sources. So that would be a big tank, or located along the length of a drift or a tunnel underground, potentially a large spill. So 1,000 microsievert per hour is certainly not unfeasible in our facilities, and this begins to underscore the need for really good design and quick response to upset conditions. In terms of control strategies, we would use the same as everybody else: time, distance, and shielding. And what those would look like would be use of remote equipment to keep people away from the sources of radiation, particularly the ore. We can use shielding in the form of shotcrete, which is basically a spray on concrete that we put in our underground tunnels. And in some of the higher grade mines, we actually use the rock itself as a shield by mining and putting our tunnels into clean rock. The next source is long-lived radioactive dust. As I mentioned, uranium is not just uranium. It contains all the decay products of uranium-238 in the ore. And of those, we have 5 long-lived alpha emitters present. In terms of dose, what that means is a 20% ore grade has the same dose potential as inhaling pure uranium ore concentrates. LLRD is generated by active means, people or machines doing things. So as an example, blasting or drilling in rock, grinding or welding on equipment or tanks to do repairs, even cleanup activities and potentially doffing of PPE could create elevated conditions and potential for measurable dose. And our final source is radon and ultimately radon progeny. The way we get a radon enters our mine is primarily through water. So water will travel through the ore body, picking up and building up radon-222 as it travels. Once that water gets to our mine workings, the pressure that kept it in solution is released, and that radon can then enter the air. We can also generate radon through any kind of rock disruption, like fracturing, blasting, or drilling. To give you some perspective on the amounts, radon gas and water measurements have been over 1 billion becquerels per cubic meter, so it can be a fairly active source term. Once the radon is in the air, it's also going to be decaying into its short-lived decay products, or radon progeny. We want to keep our mine workings, of course, very low in terms of radon progeny concentration. Our goal is less than 0.1 working levels. But because of that very high and variable source term, we can certainly see 100 working levels or even more fairly quickly. So we need to be aware of that and be adapting to those situations very quickly. The controls for both LLRD, radon, and radon progeny are very similar. Our primary control is ventilation. High volume, single pass air, and what that looks like is air comes into the mine through our intake shaft, very quickly sweeps the workings, picking up those contaminants, and then exhausts it out of the mine. We can use remote equipment again to keep the workers in fresh air and away from the ore and the source terms. And additionally, containment and confinement techniques like piping and grouting to divert that water and radon, or even ground freezing to completely prevent the movement of water through our workings and our ore body. So bringing that all together, what is it going to look like? Before we do something, be that a new mine, a new area, make a change, we want to have an idea what those source terms are going to be, estimate their magnitude and locations. For gamma, we use tools like MicroShield or MCNP for shielding, and we've developed some internal software specific to us for modeling our underground mines, taking into account our design, our ventilation, and our source terms like emanation from the walls, point sources, and that kind of thing. All of this helps us inform our mine design, our layouts, and our mining methods. So what does mining actually look like? So in a Rabbit Lake mine where it's low grade, in our estimation, you can get much closer to the ore, but in a McArthur River or a Cigar Lake, you can't. You need to be away. And we use a lot of sophisticated engineering mechanisms to isolate, automate, and contain that ore, keeping people safe. The top picture is McArthur River. They use a technique called raise boring. The way we do this is to build our tunnels above and below the ore body in clean rock, using that rock as a shield. We drill a pilot hole down from the top level to the bottom level, attach what we call a reamer head, which is a large, about 8-foot metal plate with teeth on it. We spin that, pulling it up through the ore body. The rock falls down, and we use automated equipment to pick it up and put it into our processing circuit. The ore body and the water surrounding it are also frozen, adding ground stability and protection from radon. At Cigar Lake, the geology and the ore body are a bit different. So we start in the bottom, again in clean rock. We use a very sophisticated piece of equipment that I'm going to explain very simply to drill up into the ore body, 15,000 psi water to blast and chew up the ore. The ore falls down and is collected into a piping and pumping system that then takes it for processing. And I'm pretty sure our engineers would have me shot for how quickly and easily I explained all of their hard work. On the administrative side, we of course have radiation protection programs, ISO-based, and have all the controls you'd expect out of a management system. I'm only going to put in a little plug for training. Both for supervisors and workers, it's really important for us to educate them on the sources I just talked about, where you can find them, what they're going to look like, and how you can remediate them to really bring them into our program and make our RP program active. Another administrative control that's pretty important to us is a radiation work permit. Anytime you need to do work in an area where conditions could be elevated or the task could create elevated conditions, we use a permit. We work with our crews and our supervisors to understand where they're going to be, what they're going to be doing, so we can apply the right controls to the job. Examples would be things like additional ventilation or capture ventilation, so we can duct away anything that might become airborne and be a hazard to workers. It could be shielding, it could be the right PPE, including respirators, and what kind of monitoring we need to do for dosimetry and ALARA. We use this tool to both know who's there, who's doing the work, and to calculate the dose from the tasks that these people are doing. Another critical control for us is called a code of practice. It's a standardized set of responses to escalating radiation conditions. We have a code of practice for all the source terms I talked about, but I'm going to focus on the one for radon progeny because it's our most variable source and one we really actively engage our workers in. I'll explain those colors in a minute. The key point behind the code of practice is we know what to do as conditions escalate. Workers need to stop working. We need to start investigating what caused the problem to remediate it. And as conditions rise, they have less and less time to do so before bringing in the radiation department. We also have escalating notifications internally and outside the company as well. The colors are where we bring in our workers in a much more active way. Radon progeny, as I said, is a variable source, and we have continuous radon progeny monitors placed throughout our underground workings. These sample the air continuously and tell the worker what the concentrations are through a simple light coding system. When everything is great, and we're in the green. So it starts as a green light. It would progress through to green and amber together, amber, amber red, and finally red. At red, everybody needs to leave immediately. Workers are trained on how to apply this. They have the little cards to go with it. And we really need them to understand how to apply those RP strategies, finding and remediating sources I mentioned. And these monitors also let people know both the conditions that they're in and, because you can see it from far away, conditions that they might be going into before they go into those conditions. We, of course, have a full dosimetry system. Standard OSLDs are worn by all our workers for gamma dosimetry. We have an instrument called a personal alpha dosimeter that's used for radon progeny and long-lived radioactive dust dosimetry. It's provided by the Radiation Safety Institute of Canada and licensed by the Canadian Nuclear Safety Commission. Workers wear them at all times when they're underground working, and it continuously samples the air that they are breathing. It then essentially estimates a cumulative dose that the worker would have received during the entire wear time, and typically that's a 1-month time. Radon gas, by comparison, has much lower dose, so we use a time card area system where workers are and for how long, and a grab sampling method to estimate radon gas doses. And just to give you an idea of what our doses actually are, these are for the last full production years of MacArthur and Cigar. As you can see, the average dose is significantly below 1 millisievert per year, and our maximums are 6 and 7.2. For reference, the dose limits are 50 millisieverts a year and 100 millisieverts over 5 years. I have also included a breakdown of the doses by source term. They're a little bit different site to site, and that speaks to things like the mine layout, the geology, the mining methods that we use. They're fairly comparable, but there are differences site to site based on some of those factors that I showed earlier, like how we actually mine. So to conclude, while it can definitely be challenging, doses can be managed even in very high-grade underground uranium mines through a combination of physical controls, work practices, administrative controls, and worker engagement in that whole process. Our doses are well below the limits, but that doesn't mean we aren't always looking for ways to improve. Maybe some future presentations, we're looking at a lot of things around automation, connectivity, gathering information, and how do we actually bring that to the workers in a digestible way that they can use in the workplace. And that is it for me, and we'll take any questions later on. Thank you.
So we'll do questions at the end of the session, sorry. So for the next speaker, it's my pleasure to be able to introduce Ryan Cook this morning. He is the Radiation Safety Officer and Health Physicist with Laurentis Energy Partners, which provides nuclear services across the nuclear fuel cycle. He's obtained his degree in Health and Radiation Physics from Ontario Tech University, and he will be presenting the findings from a large volume sorting and segregation source term characterization project on low-level waste from CANDU nuclear power plants. Ryan?
Excellent. Thank you. First off, I'd just like to express my appreciation to the ICRP for providing the opportunity to present today. Very happy to be here with this passionate, like-minded group of RP professionals. Okay, first off, I'd just like to provide a quick overview as I acknowledge that there are some people in the room who are not necessarily familiar or may not be familiar with Laurentis Energy Partners. So Laurentis was founded in 2012, and we are a commercial subsidiary to Ontario Power Generation. Originally, we were named as the Canadian Nuclear Partners, or CNP. We rebranded to Laurentis Energy Partners in 2020. As you can see from the global map there, we have operations located across Canada, so primarily Ontario, so Pickering, Hamilton, Port Elgin, Toronto, as well as the East Coast to New Brunswick, and we have 2 offices located in Romania. As a total, we have approximately 180 staff currently with Laurentis, and we're growing. Okay, a little bit of a background to what I'm going to be talking about today. Before I jump into this slide, I'd just like to kind of talk about low-level waste in general, and it's a good segue from Scott's presentation from Darlington Refurbishment. So low-level waste is generated during operation, outage, and refurbishment activities of CANDU nuclear power plants. So you can imagine all the work that Scott had talked about, individuals working in the reactors, taking apart components, doing inspection activities, etc. There's production of a lot of material coming out of the reactors, out of the decommissioning operations and outage activities. Pickering at OPG has been in service since the 70s, and that means that we're approximately 50 years of operation of Ontario Power Generation CANDU nuclear stations. So you can imagine over 50 years of operation, there is a generation of significant low-level waste. Just a little bit of a visual here. In total, from a volume perspective of low-level waste that's been produced over that duration, it's approximately equivalent to about 40 Olympic-sized swimming pools. So significant volumes, and that's low-level waste that ranges anywhere from brand new to 40-plus years of age. So specifically to the Clean Energy Materials Sorting and Recycling Research Initiative, it is a joint project between Laurentis Energy Partners and McMaster University, and its focus is research and development towards CANDU-generated low-level waste minimization strategies. So, the project statement is there is obviously a large volume of low-level waste that's been generated over the lifespan of the Ontario CANDU nuclear power plants, and we're looking at opportunity to reduce that volume, as nuclear waste is obviously a very significant public challenge with nuclear and nuclear operation, as well as we move into new nuclear in the future. So some background on the CMSR laboratory. Laboratory design actually started in April 2020, so keep in mind April 2020 was the beginning of the COVID-19 pandemic, so a challenging time to start a new research initiative with multiple organizations involved. But nonetheless, started in April. Construction of the laboratory actually started. It was a quick process, started in August of 2020. So we're located in Hamilton, Ontario. Licensing of this laboratory started under McMaster University's consolidated license. So we were added to McMaster's license in October of 2020, and the laboratory commissioning took place in November of 2020. So pretty quick turnaround to go from starting point of not necessarily having a rigid plan in place to design, construction, commissioning, and then we started laboratory operation in November of 2020. So laboratory commissioning, just like everything else we're doing, we're kind of taking a gradual approach to increasing our capacities over time. So we started operation at a basic level lab, and over time, after demonstrating and collecting research and understanding a little bit more about the low-level waste as it's coming to us, we were able to increase our capacity. So we transitioned into an intermediate level classification laboratory in December of 2020, and containment level in November of 2021, which is what we're currently operating under. License transition from McMaster University's consolidated license to LEP's NSRD license took place in January of this year. Actually, at that point in time, I was formerly working with McMaster University supporting the project. I transitioned over to Laurentis Energy Partners at that point when we actually got our own license, and we've been operating under our own NSRD license ever since. So some pictures on the slide to give you a little bit better of a visual of the laboratory itself. The top picture there is kind of the entry point to the containment level lab. It's a tent, it's a ventilated structure. You can see we have airborne monitoring, sampling equipment. On the left of that picture, we have HEPA filtration. At the top of that picture, exit monitoring equipment as well. A high-level floor plan overview is provided in the center of the screen there. The tent is split up into two separate areas. We have what we call the receiving area and the sorting area, where we're initially bringing in low-level waste, doing the receiving activities, making sure that there's nothing unanticipated in the bins, and then we progress to the sorting area where we actually sort and segregate, which I'll talk to in a little bit more detail. The other two pictures are pictures of the team. So, there's approximately 25 radiation technicians who are working at this project, working Monday to Thursday, 2 different shifts. So there is a team. It takes a lot of work to sort and segregate low-level waste. So important to recognize the team and the team efforts there. So one of the primary rations to this project was the research, or is the research component. So we have 2 primary research projects that are being led by McMaster graduate students and professors. So I'll talk to those quickly in a little bit of detail here. So we have the first research project, which is source term characterization and real-time analysis. So it's actually split up into 2 different parts. Part 1 is the actual source term characterization component, where we're doing alpha, beta, gamma spectroscopy of representative low-level waste swipes and samples. So currently, our approach to characterization of low-level waste through the parent Ontario Power Generation is taking a dose rate conversion factor to quantify activity based on representative swipes and smears at the station. So that's going to the primary heat transport system at the nuclear generating stations, using the full distribution of radionuclides present in that source term and distributing that to low-level waste. We've acknowledged that that is a conservative approach, and we're seeing that through our research that we're collecting in Hamilton. So first part of the project is to better quantify the source term characterization through a large-scale sample collection and analysis, as well as hard-to-detect analysis. Second phase of this project will transition into MCNP modeling for detector design and optimization. The goal here is to allow us to actually bring in low-level waste bins, collect a measurement using MCNP modeling to help us segregate at a higher level. So without actually going through the bins, going through the low-level waste bags, opening everything up, we can do a measurement initially to allow us to segregate the material before even opening the bin. Second component of the McMaster research studies is related to machine learning and automation. So as mentioned, it takes a lot of work to sort and segregate low-level waste. We are looking for opportunity continuously to incorporate machine learning automation, and that is one of the focuses of the McMaster research studies. In addition to the academic studies specifically, there's been a ton of operational data collected through the 2 years of operation in Hamilton. So large-scale data collection. So we've received about 3,000 low-level waste bins to date. Low-level waste bins are on average 2 cubic meters volume-wise. So that just provides some perspective there. But for each bin, we're collecting tritium, ambient tritium measurements. We are collecting dose rate surveys, contamination surveys, weights of the material, vintages of the materials. That's all being recorded in a local database system for tracking purposes. In addition to the bins themselves, we've actually sorted and segregated 70,000 low-level waste bags. So individual bags where we've collected contact, working distance, dose rate measurements, tritium concentrations, activity measurements, weights, material descriptions, as well as the segregated pathway. So a lot of data being collected and stored in a local database, which is allowing us to look for new opportunity to minimize our low-level waste in Ontario. In addition to the data collection, operational experience. So actually going through these processes of taking low-level waste from operating nuclear stations, sorting, segregating, material transfer is a big one. Background management is another big one. We have, low-level waste bins in multiple different areas, and the backgrounds are impacting our instrumentation, and our technicians have to learn and adapt to that. So a lot of very significant operational experience that has been learned over the 2 years. So specific to the sort and segregation, picture on the top right here is a standard bin that low-level waste comes in. This is golden standard. This is the best case scenario. Typically, it does not look this nice. To put some examples out there, we opened one lid and there was half of a scissor lift on its side in the bin. So the amount of, or the variation in low-level waste in itself is significant, and that is a big data collection point that we're putting together in Hamilton. The picture below that provides some of the ventilated enclosures. So we have 15 ventilated enclosures in our sorting area. The technicians will take an individual bag, bring it to a ventilated enclosure, and that's where they're segregating it into the different waste streams. So I didn't touch on the waste streams, but we have a washable radiological personal protective equipment waste stream. So that's your anti-C coveralls, your booties, your gloves, laundry bags. We have an incinerable waste stream, so that's your Maslins and Tyveks and microfibers. We have compactable waste stream, metal and a non-processable. Non-processable is something that needs more work, research. Eventually, there will be development of processes to allow us to deal with non-processable material in more detail. So some of the quick radiological protection metrics here. Collective radiation exposure clearly is very low cumulatively throughout the lab. So you can see first year 6.8 millisieverts collectively, second year 12.4 millisieverts. Remember, there's about 25 technicians that work in the lab, so on average less than the public dose limit in Canada. Some more metrics. Individuals who are sorting and segregating the low-level waste are wearing personal air samplers when they're doing this. So we've analyzed 4,400 personal air sampler filters throughout the 2 years of operation, which is a significant data point. Bioassay samples for tritium-specific identification, so over 1,000 bioassay samples, whole body counting, and the lab itself and the collection of various radiation instrument surveys. So, airborne sampling is a good one, and airborne monitoring. We do both ambient tritium and airborne particulate monitoring within the tent in local areas, as well as exhaust sampling. Some of the key findings that we found in the 2 years, low-level waste material variability. So I kind of provided that with the scissor lift and bag comparison, but there is significant variability in low-level waste. You can imagine from the last 40 years, processes, regulations, standards have changed a lot in low-level waste, streams at the sites themselves. There's now a likely clean waste stream, which was not always present. So there's a lot of variability in low-level waste in itself, and we've seen that through our processes. In addition, processable material within non-processable low-level waste. So the ability to actually remove incinerable material from a non-processable bin, there's significant value in that because you can actually volume reduce the incinerable material. In addition to that, the presence of non-contaminated material within low-level waste. I'll talk to you here. So these pie graphs here provide some of our assumptions from processed volume reduction. So if you look at the over 3,000 bins that have been sorted and segregated in Hamilton to date, you can see the breakdown of waste streams on the left-hand pie graph there. If you consider the volume reduction assumptions in the top, so incinerable, significant volume reduction, compactable, washable RPPE, significant volume reduction. After processing that material, we're looking at about a 50% volume reduction. So that's reducing that initial 3,000 bins to about 1,500 low-level waste bins. Remember, about 2 cubic meters per bin. So significant value in sort and segregation alone. Running out of time, but for development. So we are looking at segregating non-contaminated material from low-level waste. Breaking this into three different phases. Phase 1, we're looking at surface contaminated materials, so that's your large metals that are surface contaminated only. And phase 2 and 3, we will be looking at volumetrically contaminated material, unconditional clearance levels and conditional clearance levels. We will continue R&D, so source term characterization. There's obviously a lot of sample collection and analysis that needs to take place in order for us to have a representative data set. We need to continue to collect a lot of samples and swipes and analyze those swipes to allow us to better characterize low-level waste. Also looking at new technology and equipment, so we're looking at new instrumentation to adapt and allow us to expand our material release initiative, so cylindrical probes for scaffold tube monitoring, the internal surfaces which are currently inaccessible, as well as hoisting and rigging, craning equipment to allow us to remove heavy material from the bins. So that's what we expect the pie graphs to look like once we incorporate our phase 1, 2, and 3 material release initiative. We're really looking to further reduce that volume reduction and allow us to reduce the footprint of low-level waste in Ontario. Okay. Well, thank you.
Thank you, Ryan. It's my pleasure to be able to introduce John Takala to all of you this morning. John has more than 30 years of experience in the uranium industry at Chemical Corporation. He started his career as a health physicist and now leads a team responsible for the corporate programs for safety, radiation protection, environmental protection, quality, and audit for Chemical Corporation. He's a member of the World Nuclear Association Radiation Protection Working Group, and he's also a member of ICRP Committee 4 since 2013. John?
Thank you. I'll be speaking today with my ICRP hat on as the chair of TG 97, the application of our ICRP recommendations for surface and near-surface disposal of solid radioactive waste. The task group's mandate is to prepare a publication that describes and clarifies the application of the Commission's recommendations relevant to surface and near-surface disposal, looking at protection of workers and the public and the environment, and the report is meant to be a companion to publication 122, which is focused on deep disposal. The goals and objectives provide recommendations how the fundamental radiation protection principles are to be applied over the life cycle of a surface and near-surface disposal facility, including transitions from planned to existing exposure situations in the case of a loss of institutional control, explore the application of the graded approach in implementing protection principles and advice in all facets of the facility's life cycle, consult with regulators, implementers, and relevant stakeholders concerning practical implementation of the Commission's recommendations, and then, of course, create the new standalone publication that complements publication 122, and consider previous ICRP publications and recent international experience. As a background, the final management solution for radioactive waste is the placement in an engineered facility without the intention of retrieval, disposal. And we have this graphic in the draft report talking about how management of waste refers to the whole process from generation to the disposal. The report itself is on the last box, disposal, but we note the importance of optimizing and considering all aspects of the entire generation process. All exposure situations offer the prospect of generating waste. The management of a near-surface facility largely follows principles and practices applicable for a planned exposure situation, have to consider the appropriate timeframes and uncertainties. The recommendation applies to design, construction, operation, closure, and post-closure phases of disposal, and it doesn't consider pre-disposal management, and nor does it provide any specific guidance on siting, but it is mentioned obviously as an important issue. Now I'll just give you very high-level sort of table of contents in terms of how we've broken up the report and what we discuss in it. We start with an overview of radioactive waste and near-surface disposal, talking about waste types, generic disposal systems and options, and how that can be used for a near-surface facility, and then the phases of a near-surface facility, which is put in this schematic. We've got, in the report, we talk about pre-operational, operational, and post-closure. And then we've got, on the top part of the graph, we have the various life cycle activities, which can be concurrent with each other. And then the bottom part of the schematic talks about the various protective activities going on, and then truncated or highlighted the decision points along the way of the life cycle. Next, we talk about the application of the system of radiological protection. We cover the principles of the RP systems and note ethical considerations applicable to near-surface facility. We discuss exposure situations, dose and risk concepts. The representative person spend quite a bit of time talking about optimization of protection, and then talk about the protection of the environment. At the risk of showing a summary table without any of the context in the text of the document, we summarize with this table showing with the phase, pre-operational and operational, and then post-closure, look at the activity or scenario that we're discussing, the protective approach, the criteria used, and then within the planning framework, is it from a design basis or beyond design basis situation. Then we go to the implementation of the system of radiation protection to the different phases. We talk about oversight, protection during the different phases, and how the focus shifts when you're in pre-operation, operation, post-closure, and then protection of particular circumstances, disruptive events, human intrusion. And the report starts with the main points, which will be the wrap-up for my talk. The system of radiological protection applied to the near-surface disposal is in the context of a planned exposure situation with appropriate considerations, timeframes, and related uncertainties. Potential exposure to humans in the environment associated with the expected evolution of near-surface disposal facility is included in the design basis and are considered as a planned exposure situation. Optimization of radiological protection is essential throughout all phases, but is particular importance in the design phase, as this will determine the performance of the facility in operational and post-closure phases. Optimization, when applied to the development and implementation of a near-surface disposal system, has to be understood in the broadest sense as an iterative, systematic, and transparent evolution of protective options for reducing impacts to humans and the environment. Picking up on the theme of transparency, the appropriate mechanisms for formal and structured dialogue between regulator and the operator and stakeholders should be established as early as possible in the process. We note the inclusion of ethical values in the dialogue is important and can be useful at promoting a shared understanding. The uncertainties associated with future exposures must consider both the magnitude and the likelihood of occurrence, and scenarios involving human intrusion require special consideration. The report we hope to be able to release for public consultation in the near future. I've been working on it for a number of years, and COVID didn't help. And this is some of the team when we're visiting Fukushima Prefecture, looking at some of the challenges in near-surface disposal and how they're dealing with it as a result of Fukushima. Thank you.
Thank you, John, for your presentation. Now we'll go on to our last presenter. It's my pleasure to be able to introduce Dr. Marcel Lips to you this morning. Marcel is the Director of Chemistry and Radiation Protection and also Deputy Plant Manager for KKG in Switzerland. He has more than 30 years of experience working in the nuclear industry and has been the chair of the World Nuclear Association RP Working Group for the last decade. John?
Thank you, Chair, for your kind introduction. Good afternoon, ladies and gentlemen. I will present today some experience we made in optimization, some upcoming challenges we had in optimization, as well as with low-dose decision-making. I will also include a little bit of points that we see with the public perspective and with practicability in our actions. So I start with a graph that is maybe not so famous and helpful for shareholders of a company. But for us as RP professionals, we like these kind of graphs. And I want to say with that the nuclear industry has, in recent years, had a good performance and due to optimization, and was able to reduce either individual and collective doses over the years. Just to illustrate that, I have plotted on this slide the progress achieved in nuclear power production. This is from the latest ICRP data. So for PWRs and BWRs as the most common reactor types, you can see that the collective doses dropped significantly over time. And it is to note that this happened despite an aging fleet, which is turning more and more into long-term operation, needing more maintenance and more safety retrofits. The same can be seen for worker doses. This is from the latest UNSCARE report. Current worker doses are comparable to natural background radiation. Mean individual doses are now far below 1 millisievert a year, which is more or less within the variability of natural background radiation. Impacts to the environment are well controlled, and public exposures are in the order of a few microsieverts per year for the most exposed persons. And that makes no difference to their total radiation exposure they get from natural and medical sources. Unfortunately, accidents are not part of the good record. And we have seen that such events do have tremendous impacts to society. We heard yesterday in a presentation that often the harm is anything else than radiation. And this is a good example on how to deal with optimization and what the challenges are with optimization. How far should we go to protect people from radiation, but to give them other hazards and other harms which are not radiation. The key for the good record we achieved is mostly ALARA and optimization as given by ICRP 103. We have seen many examples during the previous presentations. There are some 2 other examples here, like the use of specific shapes for nozzles made out of lead. Nozzles often contain smaller hotspots to be covered, or a combination between water in components and lead shields on components. And in many times, we can achieve dose rate reductions at workplaces of more than 1 order of magnitude. And there are many other types of engineering controls. I do not want to go into detail. We have seen a lot of them. Personally, I think there is an upcoming new technology with digitization that will have the potential for further optimization, for further dose reduction. And I'm thinking about remote monitoring possibilities, about training and pre-job activities, and especially on virtual training. And just as an overall message, well, it's clear all this works well, but it works only well when leaders and workers are committed to a strong safety culture and do support all these education training programs associated with it. In the industry, we have right from the beginning on, we have involved the workers in the ALARA process, in the optimization process. And not only the RP workers, all workers that are involved in a job. And that helps them to get familiar with the process, with optimization, that helps them to get familiar with radiation. And we heard yesterday from John Takala, by doing so, they do not have any problem with their radiation exposure. But this is different with the public. These few microsieverts they get from the nuclear installations are the smallest fraction of the total exposure. But often, it's the fraction that is questioned the most. So, in fact, here we have a communication issue. The optimization we've done to protect the general public has risen in a communication issue. Not only for the industry, I think it's for the whole RP community. And another part might be the system itself. I'll come back to that in a second. The public is often not aware about natural background radiation. If you go out to the street and talk to them about natural background radiation, I've seen many question marks in their eyes. And many of them do not know about the use of radiation in medicine. But of course, they know that in the nuclear industry there is radiation. And this is another part of the communication issue we have. And the system is complex. We have heard that many times this week, the use of dose limits, constraints, reference levels, and its varying applicability in plant, emergency, or existing exposure situations are confusing, especially for the public and to some extent also for RP practitioners. And complexity decreases practicability. So some kind of simplification would be well appreciated by the nuclear industry. At the beginning and in earlier years, our ALARA process, optimization process, was mostly RP-centric. And the results, I have shown that they are good, but the lower the doses now become, the more other hazards need to be regarded and to be implemented in the optimization process. So we began as an industry to look in a broader way to the optimization process in a let me say, in an all hazards approach. And just to make clear, it is also my job as a representative of an employer. It's my responsibility to make sure that nobody gets an overexposure, that everyone is protected against chemical agents or conventional safety and what else we can find. So the problem here is we have good guidance from ICRP how to perform optimization in radiation. I have another field of regulatory guidance on how to protect people from chemical agents. And there is another area of guidance on how to deal with conventional safety, but they are not harmonized. That is the problem for the industry, and that will just lead to a situation that I will have a solution for that issue that might be different from other ones. We will have different solutions in different countries, maybe different solutions even in the different installations in the same country. And I'm afraid that this will arise new questions because it's unclear to the public, it's unclear to the practitioners, and here I think some kind of harmonization and connections between all these regulatory fields is really required. Just to show, I come back to these lead shields I showed you before. This is a very simple example. These shields, they need to be mounted mostly manually by workers. So it's a radiation protection measure that introduces new ergonomic and conventional safety risk. And it's regulated in 2 different parts of the whole complex regulatory paperwork. So these are challenges we are dealing now today when we go further with, and when we have reduced all these doses to the workers. And it applies also to the public. Public is exposed to different hazards like radiation, air pollution, climate change, and so on and so on. And we know, or we are aware, that climate change is causing a tremendous impact to our society and the planet, far more than any small change in radiation ever will. So in fact, ICRP here should take greater effort that the system is not only radiation-centric. We need a system that facilitates the interactions between the different hazards for optimized overall safety. It won't be ICRP's task to deal with chemical issues and all these issues, but we need these interactions and these interfaces to other areas of expertise. Furthermore, today our RP decisions in practice mostly are at very low levels of exposures, where risks are uncertain and our actions may be not proportionate. But it's necessary according to the L&T approach. And again here also I think we need a little bit a wider context for proportionality. A graded approach could be potentially the however in practice. Nevertheless, World Nuclear Association supports the L&T approach. It is just to note that it's not a theoretical hypothesis. It's just a simple model on which to base a system of protection. And there's no claim that every type of radiation is linear all the way down to 0. Some may have more linearity, some may have less, and some may even have a threshold. And that's the reason why we need a simple model. But L&T also reinforces the belief that risks at low levels might be significant. And this could be another aspect of the public microsievert perspective. A graded approach with less attention to low doses will concentrate the optimization where benefit is biggest and will prevent practitioners from too much paperwork at low doses. Another example of a working place, we've seen many of them. It's big. There are several sources around. There are different dose rates at these several sources. There might be different levels of contaminations and even changes over time. This is anything else than laboratory condition. Practitioners in such a field, they need few simple variables to give adequate protection in due time, especially when changes occur. More heavily based protection system, a gender-based or age-based or even individual sensitivity-based system is interesting from a scientific perspective, but is simply not manageable in such a field. For the same reason, we need to carefully consider the implementation of the new dose quantities. We've heard from Thomas Otto that for the nuclear industry, at least, the changes will be very small, and the benefits might be even less than the additional expenses. And that will cause doubts on this implementation. So for us, it's really important that any changes to the system, any changes in practice has a clear benefit to health and safety, and is proportionate and practicable. That led me to my conclusion. In accepting responsibility, the nuclear industry has for years controlled and reduced occupational and public exposure to sufficiently low levels such that any risk is uncertain. In the same time, the system has evolved and thereby added some complexity to it. L&T is still the best basis for developing a system, but implies a weighted bias of unverifiable risks at low doses. Other risks might be more dominant, but get less attention. For that, nuclear industry recommends the implementation of an all-hazards approach in the future system so that we can guarantee best overall safety for workers and the public. And while L&T is still the best model, we recommend also to implement a more realistic graded approach with more proportionate to risks at low doses, which is applicable to the field and less to laboratory situation. Industry is committed to an effective optimization of the overall risks and is convinced that implementing these recommended changes will attain in a proportionate balance between risks and the use of societal resources. Our association is aware about the challenges behind these recommended changes, but is willing to give practical input to that and to support ICRP in the development of the next general recommendation. And this is for us then the basis for further optimization and enhanced ALARA process. Thank you very much.
Thank you, Marcel. We'll open the floor to questions. See, we have already some.
Yeah, thank you very much. Mary Duarte, Director of RAD Safety for OPG. So I have a question and a comment. Let me start with a comment. I believe that nuclear power production has a role to play in the decarbonizing the planet. However, the question of waste is one that remains and challenges that energy sector. So I would like to congratulate Laurentis for the work that they are doing in terms of segregating the waste and the desire to continue those efforts. I think it will serve nuclear power production well. So congratulations to Laurentis. Now for my question, it's directed to Carrie, related to the uranium presentation. So Carrie, my question is around the behaviors of the workers. And I was thinking about your system of safety lights, when you have a light or combination of lights, etc. Do you feel that those workers are meeting your expectations with respect to standards around response, for example, to those safety lights, to talk specifically? But generally, is your organization satisfied with the worker behaviors and practices? And when there are challenges, do you have any insights that you can share?
So I think overall, yes, we are happy with the performance. It's something that we reinforce through different means, initial training. It comes up as kind of safety moment talks, and it's just something that they see on a routine basis. So it's become very ingrained, and I think because it's largely cultural. We're not perfect, of course, but overall I think they do understand how they work and how they protect their best interests, I suppose. As far as good ideas, I mean, people don't always want to stop and then start to implement these practices. So in part, top-down, so having that culture, bringing it all the way from our top management through to their supervisors and making that more and more ingrained, helping them and enabling them to identify those sources, I think is also important. So if they see a light and don't understand it, don't know what to do about it, or, oh, I just have to phone the RAD department, I don't want to do that. Making them part of it and active, I think, is a key feature in making them want to engage and do the things that they need to do.
Thank you very much.
Chris Malcolmson from McMaster University. First of all, thank you very much for the talks. I thought they were terrific today. I just had a quick question for Ryan, and maybe Joe might want to pop in. We've heard a lot this week about community engagement, communication, transparency, things like that. And you had a slide that described a timeline of going from, design of a research facility through construction during a pandemic to first operation only a couple months later. Wondering if you might be able to give some advice on the communication strategies that were used for engagement with the community that allowed buy-in for a waste handling facility in a major urban center.
Thanks, Chris. I can start, but I'll lean on Joe for some of the other additional ones that I wasn't a part of. But I'd say it's a great question. Overall, there's a lot of aspects of what we're doing that involve, that transparency communication piece. And that's another challenge, that is identifying the stakeholders involved in some of those conversations. So like you said, city member, like Hamilton City. We also have leaseholder, right? We're in a lease agreement, so it's the building owner. We also have Ontario Power Generation as the parent, and internally Laurentis Energy Partners and McMaster University. So there's a lot of people who are involved in this. And that conversation is very important, and we're seeing it in many aspects. I can turn over to Joe for the specific commissioning side of it, but I know even some of our engagement for our material lease initiative, identifying who the stakeholders are and presenting those and being open to them. So, we are continuously having conversations with regulations. We brought the material lease initiative to key stakeholders within OPG, the RP groups, the responsible health physicists, the executive committees, having those conversations. And, we've just been really open with what we're doing and the trajectory that we're trying to achieve in terms of making a difference, and really coming down to there's opportunity to support with low-level waste volume reduction, and here's what we're trying to do, and this is what's involved in that. And yes, there's a lot of key stakeholders that we've been in constant communication with. Joe, anything to add there?
In the interest of time, I'm not going to add too much to that. I think Ryan did a good job on that. I would just say that a lot of people outside of nuclear don't get too excited around nuclear waste, right? And if they do get excited, it's usually not in favor of nuclear waste. So I think the one thing that was really interesting with this project is that we did this project in a building that used to be the newspaper printing facility for Hamilton, right? And it was still had journalists there, right? But identify them as stakeholders, got them involved, and explained to them and everyone else as to why is this not just an OPG issue? This is an Ontario issue. This is a world issue. How do we manage this better? And when we explained that to them, the journalists, we brought them through, we explained what we were doing, why we were doing it, and they left, and they wrote an article that was amazing, and it was really balanced and really fair, and just said, hey, we understand why this is important, and we're happy that the university and the organization and Hamilton can play a role in trying to deal with this. So I thought it was really good, but it's really just about, exactly like he said, stakeholder relations, getting them involved, working with them together. It's the only way.
Thanks, Jeff Doviak from Shared Health. So my thanks to the presenters. Coming from a healthcare background, really the only time I ran into NPP or fuel cycle is at a symposium like this. So I got something out of the session, including the questions for Scott, Carrie, and Ryan, and they'll be really quick. So for Scott, approximately how many electronic personal dosimeters would you start a refurbishment project with? And was it hard to get that many? For Carrie, my question is, your continuous radon progeny monitor, is it just a visual display or something else? And for Ryan, did you run into much of an incident of either hand contamination to your staff or hand injuries? And if there were hand injuries, what did you do to mitigate that?
Okay, thank you. I'll start. Prior to the start of Unit 2, we had procured approximately 3,000 dosimeters from external suppliers. We had the benefit of Unit 2 that there was a 5-year planning cycle with lots of time to assess and determine how much you needed and procure it in a timely manner. I'd say we're probably in the neighborhood of about 4,000 active dosimeters now with the 2 units overlap and the work occurring at the same time. So.
All right, and my answer is yes, it does do more. The instruments record the actual radon progeny concentration. They log it, so it's a downloadable piece of information. But to make it more accessible, we've just displayed it through a light system linked to the code of practice.
Thanks for the question. Relatively quick answers. Hand contamination, not a significant issue at the lab. Programmatically, there's been a lot built into how we're sorting and segregating and the RPP that we're wearing, as well as the background of our radiation technicians. We have people from Class 1, people from the other aspects of the nuclear industry, people with very technical backgrounds. So all of that comes into to really supporting the program and making sure that we're containing contamination at the source. In terms of hand injuries, we can take that offline. We actually have operations manager attending as well. Definitely a lot of lessons, and it relates to Miguel's presentation in terms of the conventional and radiological kind of interference there and how to, make everything kind of blend together, but definitely a lot of lessons related to hand injuries.
We're between where everybody's very patient and nobody's making a dash for lunch. But we are a bit over time, but we'll try to have a couple more questions, and I think everybody's probably pretty keen. They'd be happy to answer questions over lunch. Mike in the center.
Okay. My name is Mike Gray. I'm a health physicist and occupational hygienist who recently retired after about 40 years in the nuclear industry. There's been something that's been bothering me this entire week, and I've been thinking about it all through the presentations. And our final speaker mentioned it, so I thought I'd follow up on it directly right now. I've been very much aware of how much both radiation protection and the other branches of environment, health, and safety are often struggling with the same issues and dealing with them back and forth. And I remember earlier this week when I listened to the talk about ethical issues in radiation protection, I was constantly thinking that early in my career, I spent a lot of time dealing with the recommendations of the Ham Commission in occupational safety, who covered much of the same territory, came to many of the same solutions. This was nearly 50 years ago. Yet when I looked at publication 138, I didn't see any mention of the Ham Commission or their work in that publication. I was thinking earlier this morning when we talked about the issues over LNT, that when I work in occupational hygiene, the pharmaceutical industry had the same issue. They dealt with it by developing an approach called control banding, which is widely used in occupational hygiene now. It's a technique I use quite a bit. I really like it. It's very effective. But I'm willing to wager that most people in this room have never heard about control banding and have no idea how it would be used or how it could be applied in radiation safety. And finally, I was thinking over the years, I've done a lot of work in air sampling. I've measured a lot of particulates over the years. Some involved radionuclides, some don't. And I look at the way occupational hygiene and radiation protection treat air sampling and the assessment of those hazards, and I see that both fields have half a solution. It would be really wonderful if they'd actually get together and talk to each other. So we've mentioned a lot about communication over the years, or over this week. I'd like to suggest that what we really need is communication between the very closely related branches of the environment, health, and safety field. I find that one branch is struggling with problems that other branches have already solved. We seem to be working at cross purposes and a lot of wasted effort. And like our last speaker, I'd like to suggest what we really need is a holistic approach to dealing with these issues. And I think that ICRP is a very respected organization in the EH&S field, is probably the one that's best placed to take a lead and try and build up this communication between the fields. So I'd like to ask if the members of the ICRP would consider taking that on as something they would do in the development of the next set of recommendations. And there really is no question here. I just wanted to get up on my soapbox for a few minutes. So thank you for listening to me.
Okay. A question, short?
I will be short, okay. So the question is for Ryan. What do you do with the waste? What do you do with it? And the second question is, you mentioned Romania. Do you know if there is a similar program in Romania for waste?
Maybe I'll go Romania first. We can take that one offline.
Okay, sure.
There isn't, but we can talk about that over lunch. In terms of where does the waste go? Waste goes back to the generator. So it goes back to the generator for processing, whether it's incineration, compaction, metal melt, laundry.
Thank you.
Thank you.
I think we'll call, we're 6 minutes over. I think everybody will want to, I think everybody's willing to answer questions over lunch.